Welcome in this video where we are going to implement the famous LSGAN paper. So it's a paper from 2017. At that time, GANs were suffering from mode collapse. So yeah, at some point during training, for example, they were collapsing and always producing the same value. For example, here we have an example from the paper, and these are the results we'll get by the end of this video. So this is the GAN train after 40k epochs, but this is very close to the target distribution. So let's assume for now it's the target distribution, and therefore we have a multimodal 2D distribution. And usually GAN tend to collapse to only one of their mode. So this is a well-known issue, modes collapse in GANs. In that case, this is the training of the LSGAN. So this is a GAN but with an improved objective that suffers less from mode collapse. We see that after 5k and 15k epochs, they had collapsed to only two modes. So even them, they are a bit prone to mode collapse. But after 24 and 40k iterations, they recovered from mode collapse as opposed to GANs. So these are very difficult problems for GANs. It's difficult to them to learn multimodal distribution in that way when there is no connection between the modes, but in that case least square GAN is able to do it, and I think standard GAN they completely fail at it. Let's have a look at the figure from the paper. Okay, so we have regular GANs versus LS GANs, and we can see that regular GANs they completely fail at this problem, while LSGANs are able to really to learn this distribution very well. So yeah, I think I've said enough. Let's dive into the implementation. So if we move on to the implementation, we'll use PyTorch, Seaborn, and Matplotlib to plot the results, NumPy for processing the data, on TQDM to see the progress during training, and also multivariate normal to create the dataset. So let's jump in and directly implement the dataset. So we'll create a function to sample a mini batch from the dataset with a given batch size and the number of mixture. In the paper, they used 8 mixture, so this is what we'll do. So the first thing to do is to create the 8 mixture. So we sample theta between 0 and 2 pi, and we sample 8 mixture, so 8 plus 1, because if we go to the paper, we can count them 1, 2, 3, 4. Okay, so there is 5 of them. Yeah, that's a good question. I will need maybe to read more or to read again the lean space documentation. Okay, for some reason we do number mixture plus 1. Okay, to make sure that it's a circular, I think. Yeah, if we sample only 8 mixture. Okay, that's a good question. I will need to double check that, but anyway, let's move on. So the first thing we do is to create the 8 modes, so creating the centers, the x and y coordinates of the modes, and then as we are sampling a random mini batch, we sample the mixture randomly. So let's say we want 1000 data, that the batch size is 1000. We sample a 1000 mixture randomly. And then as each mode is not a delta point, we have a distribution. So each mode is a 2D Gaussian distribution. Then we sample around those modes with a multivariate normal Gaussian distribution with that standard deviation, so standard deviation of 0.01. Okay, so now we are able to sample from a mini batch, which is one of the helper we need. The second helper we need is to sample from random noise. So we can create this function, sample noise, in order to sample from a normal distribution whose dimension is 256. So this is the dimension of the latent space. Now we can move on to implementing the generator on the discriminator. So the generator takes the latent space as input. So we've said that the latent space dimension by default will be 256. So we do the same for the generator. By default, its latent space input dimension is 256. We'll use 128 as hidden dimension. And for this toy problem, by default, the output dimension is 2. This is a 2D toy problem. And we use tangent hyperbolic for the activation functions. This is standard MLP in PyTorch. There is nothing much to say there. Then we can move on to the discriminator. This is the opposite of the generator. Its input dim is only 2, so it is the data dimension. Again, we'll use an hidden dimension of 128, and you can see that therefore the architecture is very similar to the generator, but with the input dimension and the output dimension that change. The output dimension is 1. It's just the score that the generator gives for given input, so it's just a scalar value. Then we can move on to training the training loop. So we take a generator and a discriminator as input. We take optimizers for them, and also we'll train for a given number of epochs. There is this well-known parameter k when we train GANs. So this is the number of times we'll train the discriminator more than when we train the generator. Also, we take as input the batch size on the MSE loss. Okay, we just created we create an object from PyTorch for the MSE loss. And then we prepare our training loop. So we create a variable for logging the results. So the generative and the discriminative loss. It is always great to separate them rather than just plotting the full loss, so that you are able, if you want to do some inspection, if you have some problems during training, you can easily check the two losses separately. So we can move on start by training the discriminator. So yeah, we've talked about this parameter k. We will iterate over a few number of epochs on training the discriminator. And when it's done, we'll do one iteration on the generator. So on average, we'll train the discriminator k times more than a generator. In that case, k is equal to 1 by default. So for the discriminator, first we sample a mini batch of m random noise. So we sample latent data, and we also sample target data, so data from the dataset with the get mini batch function. Then we will update the discriminator by ascending its stochastic gradient. So we create the score for the real data. We generate fake data with the generator, and we feed them to the discriminator, and then we also have this score for the fake data. And then this is the loss from the least squared paper. So they say, I will not go into the detail of the paper. By the way, if you are interested into that, just let me know, and I can make more videos where we move a bit from the implementation and where I explain the paper. So basically, they suggest that instead of using the standard GAN loss that is prone to mode collapse, just to take the MSE loss between the score of the discriminator to the target probability. So the discriminator for the fake data, he wants to predict 0 values. That will be the ideal situation in a perfect world. And for the real data, he wants to give it a score of 1. So we just take the MSE loss between those scores on the target values, the ideal value in a perfect world for the discriminator. And then the loss, we take the average of the two losses, the real loss and the fake loss. This average is not necessary. We could just take the sum. So doing the multiplication by 0.5 is not very useful. But anyway, it was done in my code base. So let's keep it, but you can try to remove it, and it will not affect the results. And then we can do a gradient step on the discriminator parameters just by using the optimizer. And then we can also log the value of the loss. Now we can move on to the generator on doing the gradient step update on the generator weights. So for the generator, we do not need real data. We just need to sample latent data, and then feed them to the generator, sample fake data, and then to feed them to the discriminator. Now the loss there is the opposite of the discriminator loss. For fake data, we want the generator wants that the score is equal to 1 for those, so that it is able to fool the discriminator. So for those fake data, the discriminator, the target was 0. This is this line. For the fake data, the target is 0. But for the generator, because it's a min-max game, for the generator, this score is 1. So the opposite of the discriminator. Once we've computed the loss, again, there is this 0.5 there for consistency. It's not very useful. You can remove it. And then we just update. We do a gradient step by using the optimizer. Now we can move on to combining everything. Before doing that, there is this show distribution function. So basically, in the figure in the paper, they do not show directly sample data from the generator. First, they do a KDE on top of it. So they fit a kernel on top of the learned data, and they show the distribution learned by the kernel. so that the plots are a bit more, the plots look better. So yeah, so basically they just we take data as input, we do a KD plot on top of it, and yeah, then we can just make our plots a bit prettier by removing the ticks, adding labels, setting limits on the x and y axis, and basically yeah, it's just it. So basically it will give those plots, so fitting a KDE on top of the data and then showing the learned kernel with Seaborn. And now we are finally ready to plug everything together. So we will train on GPU. If you have a GPU on your computer, that will be much faster. We'll create the discriminator on the generator, and create the optimizers. We'll use Adam. You can see that for the generator we use a learning rate that is higher than for the discriminator. I think these are the learning rates from the paper. And then we can feed everything in the training loop to train the generator on the discriminator. And then we can move on to the plots. So what we do, we plot the generator for 0, 5,000, 15,000, 25 and 40k epochs. And then we show the results for at all these intermediate steps. So what we do, we sample noise 10,000, then we feed them to the generator. So that gives us fake data generated by the discriminator, by the generator, and then we can feed them to the short distribution function. So that for this target axis, so we've created 5 axes is on that figure, and for every each of the axes we show the results. So this is what we do. Then we save the figure and we are done. So not very complicated. Yeah, the most complicated part is this loop, but if you've already implemented GANs, this is you've already seen that. You just need to change the loss. So a very simple paper, but very useful. It has had a lot of impact. It has a lot of citations. So yeah, that's it. I really hope you like this video, that it will be helpful to you in your learning, in your research. If it was, please leave the thumbs up. It really helps with this channel, and also subscribe for more content like that. Thank you again for having followed this video.